Welcome live from Brightlands Camelot campus in this masterclass by circularity expert Marijn, Rijkers. My name is Astrid Verberne and I'm Community Development Manager at this campus.
Hello, welcome. My name is Ingrid Grimbergen, Communications Manager of Camelot Insights. Let us first introduce Marijn Rijkers properly to you. The red line in Marijn's professional career has always been making chemical processes sustainable. He was involved closely with green initiatives within DSM, like green antibiotics, ethanol, succinic acid, and adipic acid. From 2013 on, Marijn was leading DSM's corporate agenda on a circular economy, where he was looking for high-quality applications like recycled and bio-based circular raw materials.
Since 2017, he is leading circularity within InnoSyn and Camelot Insight, both located, just like DSM, at this campus. And in close cooperation with Camelot Insight and InnoSyn, we have prepared this masterclass for you today.
About Marijn. Marijn is not green left nor green right. He's just green and circular and willing to give a helping hand to the industry, academia and government with his knowledge and hands-on experience to solve the green challenges this planet is facing.
And today is a special day, Marijn. Marijn will share his vision on the transit to circular chemistry and materials and what it takes to make that happen. He will share it with us today. During his talk, the coming 60 minutes, don't hesitate to ask him questions in the chat. We can all see them pass by on a big screen in front of us. And at the end of his talk, after 60 minutes, we will share with you, together with Marijn, together with Ingrid, the answers on all your questions.
So now it's time, from your home to here to Center Court, to give Marijn Rijkers a welcome on stage. Marijn.
Thank you very much, Ingrid, Astrid, for this very kind and extensive introduction. I am really very happy that I was asked, to Brightlands and Camelot to share my experiences, and I am really happy to do so. So, the storyline is that I would like to first say something about Camelot Insight and InnoSyn, my employer. Then I like to continue what it takes to move towards circularity, what kind of feedstocks are available, what kind of opportunities are there. Also an example case to make things more tangible of projects I executed with a lot of other people. Showing also the power of open innovation. And in the end, what to do to make chemical sites like Camelot more circular. And I think we have a big task, but the good news is we can do it very well. And by joining forces, a level playing field. I have indeed tens of years of experience in circularity. What I did, in fact, is putting all the inputs I got from a lot of colleagues and contacts in the external world together. And in the past years, I could compose, a kind of a vision. I'm not advocating I'm a prophet, but I think, we can say what makes sense, what are the dead ends, what are the opportunities. And I would like to share with you the view about this, but of course as input for discussion. But as Ingrid and Astrid explained, we have plenty of opportunity to ask questions, and I will make sure that I will answer them all. Starting with Camelot Institute of Science and Technology, abbreviation InSight, what we do is help entrepreneurs in sustainability, in green processes, to realize their bio-based and circular dreams. And how we do this? By providing knowledge and assets. Knowledge from the universities of Eindhoven and Maastricht, but also from industrial partner DSM, and infrastructure by piloting. Brightlands has a nice bio-based pilot plant we use for executing, showing valorizing technology which entrepreneurs will put forward and try to test. So we have very nice piloting facilities. I also see the link here to the video tour. I'm not showing this now, but I think it's a 4-minute video tour showing all kinds of equipment that we have. We have a nice big hall and very good, I would say top-notch, state-of-the-art piloting equipment where we can do all kinds of experiments. Consequently, we can do a lot of projects. Just to guide you through a little bit, livolinic acid products. That goes to adipic acid. You see here nylons as an example. We can do all the piloting for testing this process. We can go to lignin-based fuels. Lignin is often a critical, let's say, a fatal raw material, but if you can liquefy it, you can make ships sail on this. We can also valorize hemicellulose by intermediate furfural or the hydroxymethylfurane 3, making very special polymers. We can think about high performance bio-based polycondensates with smart additives, making them stronger with a high tensile strength. For instance, but other properties as well. Lignin first approach, it resembles on paper industry, but now not cellulose, but lignin is the most important starting material, and also there we can make great things from this. Also this project is successfully running in InSight. We can think about bio-based and circular engineering plastics. That is, to start with recycle PET from bottles and upcycle this by putting in nicer soft blocks so you can make better quality plastics out of this back again for reuse. And we have also lignin, but not as a fuel, but also as a plasticizer where you can mix them with other materials. So this is just, a very short view on the projects InSight is doing. The other company I'm representing is InnoSyn. InnoSyn is, let's say, the chemistry competence of DSM, which went into an independent company 3.5 years ago. And InnoSyn has a number of expertises. We do a lot in catalysis, biocatalysis, homogeneous catalysis, heterogeneous catalysis. We combine this also in flow chemistry, where we can design complete reactor systems. We do photochemistry, we do special crystallizations, also for pharmaceutical products. But last but not least, we are also driving in InnoSyn the bio-based and circular expertise. And you see on the right-hand side of the slide, there's a lot of customers. We do chemistry. InnoSyn does chemistry. InnoSyn is a one-stop shop. We start with ideas, but we can take the ideas up and including implementation in chemical plants because of our industrial expertise and experience. So that's why we have a lot of customers in very diverse chemistry applications, like agro, like flavor and fragrances, specialty chemicals, food additives, sweeteners, etc. And just to show that we are really going up and including implementation, this really requires scaling up the process. This is just a picture of our InnoSyn's piloting facilities, where we can do all kinds of unit operations, and when we can really serve the customers very well, and we can also scale them up at the client, at toll manufacturers. We have a big network in making these things happen. The bio-based and circular economy history is pretty rich. So when we were still in DSM, we did already a lot of projects. We started, in fact, already in 1994 with semi-synthetic antibiotics, with enzymes instead of organic chemistry, saving out a lot of waste streams, etc. We did succinic acid, 1,4-butanediol, valency noteketon for isobionics, right from the beginning of the company. We coordinated a study called Winning Key Renewable Raw Materials at DSM, but in fact it was much wider applicable to all kinds of chemical companies, with a lot of resonance, I would say, created. Spin-outs of this study were adipic acid, were livolinic acid. We will dive into this a little bit deeper later in this talk. Fatty acid building blocks, very important for pharmaceutical industry, for instance. Lignin valorization, and also a company, the EU project, BioForever, which valorizes woody biomass. So looking at circular economy, I always think about this domain. You have on the x-axis value creation, left side little value, right side lot of value, and on the vertical axis you have all kinds of raw materials. The green ones are bio-based, can be bioresidues, it can be crops, and on the top side we have post-consumer, can also be all kinds of waste and dirt we don't use anymore. And if you start on the left side, you go to the right side creating value. And the projects which are currently run in InSight look like this. The red area are the projects I just highlighted. Yeah? You see that on the left side, in the green area, the green circles, we have still a lot of opportunity for new projects, for other projects, especially on the side of the feedstock, and also especially when it comes to plants and crops and content base materials. And this is, I think, also an invitation, that it is really good to complete the value chain from the left to the right side by adding the right partners. So, climate. That was, of course, important. We must stop heating up the earth. In the past 60 years, during my lifetime, humanity succeeded to increase the CO2 content per square meter earth surface from 3 kilos to over 4 kilos. And this increase cost already 1 degree heating, 1 degree more. And if we are using up all the raw materials from fossil sources and just burning it and emitting it, then we can easily go over 10 degrees heating, which is a big disaster for humanity, that's for sure. So how can we stop? We must stop by exploiting fossil resources. I think it's not a new message. It is inconvenient perhaps, but it is necessary. And the good news is we have a lot of alternatives. We have circular materials from bioresidues and post-consumer. And we have energy from the sun. And in Holland we are talking a lot about windmills, but photovoltaics is really what's about. I think when you really want to harvest the energy we need from the sun, you will need photovoltaics. So, message is, yes we can, but of course we should really start with this. If you look at the Earth, the irradiation of the sun is a lot. It's a big amount of exajoule. 1 exajoule is 10 to the 18th joule. This creates biomass. Plants are growing. And you see that only 0.03% of the sun is taken up by the plants. And then we have also so-called arable potential. And I should also mention that this picture was originated by my former colleague Wim de Laat. I really want to recognize him, give them some recognition about this. This arable potential is also, again, a small part of the total biomass production. And from this arable potential, we create our food and our materials. At least we did that 2 centuries ago. And this goes to products, to dairy, to meat, to food, houses, building, etc. This was about the situation in, let's say, around 1815 or 1900 or something like that. Then we started digging and drilling, getting in fossil feedstock, oil, mineral oil, coal, and natural gas. And these resources are at least serving a lot our energy and some products. Heat, also liquid transport fuel, and also some products like plastics, etc. Well, when this was in place, then we said, well, maybe we can also use some biomaterials for our energy needs. Well, I colored these arrows red because they do require land. And this land can also be used for food crops, etc. So that's not really a desirable development. You can go to some extent, but you cannot really continue serving all the energy needs with this. So, and we started, and it's really starting, to have some green electricity, hydro, photovoltaics, windmills. So that's about the situation today. So we also like to use bioresidues, the fatal biomass, which is, I would say, not really useful for other purposes. And I think that's a very big opportunity. Well, then, if you're going more and more circular, the red arrows will disappear. We will not use energy from the land anymore. And we will go to electricity, mobility, directly created by the sun. And if we do that, it becomes more and more, and in the end, also the fossil needs disappear. So this would be the idea of a really sustainable world. You see here, energy comes from the sun, materials comes basically from biomass or circular. So looking at feedstocks, we have a lot of bio-based and circular feedstocks available at our disposal, enough to serve our material needs. Think like woody biomass, lignocellulose. I'm not talking about trees, I'm talking about forestry and management, meaning that we are well maintaining the forest. If you maintain the forest very well, it does produce a lot of branches or dead trees. And these, for chemistry, it doesn't really matter. You need only the structure from these trees. Natural oils, aquatic, seaweed, for instance, or algae. Biodegradable residues, like what you throw away at house, let's say the leaves from the food, etc. Plastic recyclates, municipal solid waste, side streams of processing industry, also paper industry. There's a lot of useful side streams for the chemistry. And last but not least, the engineered recyclers. That's really what's called assemble to disassemble. So if you're putting together a project and you're thinking ahead, that can be easily taken apart, it becomes also easier to recirculate and to use it for high value applications again. Yeah? These feedstocks look very nice, but they are quite voluminous. And they are not very stable. If you leave them on the land, most of them rot away. And rotting away means methane creation, which is a lot more damaging gas for the climate than CO2, about 25 times. So that's not the way it goes. So if you are not allowing this and you're processing this to commodities, densifying it, that it can be transported, then you're making a good step. And then that's really, the gate for access to the chemical industry. I will come back to this later. So if we have these bio-based biomass and bioresidues, how can they connect to chemistry? Well, I have a number of examples. This is, we call it the C1 tree. This goes via methanol. So you can make it synthesis gas, then you can make it to methanol. And methanol is a point of entry to the key building blocks where we make plastics from. A lot of volume, and I think the very nice story here is that this is quite also a very economic route. We can make green methanol as cheap as today's. So that means we can make a transition without, I would say, too much variable cost. You have to add a lot of capital, of course, to make it happen, but it is quite possible in the end. C2 tree goes primarily via ethanol. Ethanol can go directly to a number of specialties, but mostly you need to dehydrate it, to move it back to ethylene, and ethylene is a component which is very well known in the fossil industry, which can also connect over there. We can think about natural oils, meaning that a lot of food, of course, that is not what you would like to touch upon. There are some oils which you cannot eat, for instance castor. 10% of the is already dedicated for chemicals, and if you see what kind of tree this feeds, and that's only very a small example, that the tree is much bigger than this one. You can make, let's say, C9, C10 acids from this, like azelaic acid or sebacic acid, and also a lot of other specialties, which is also, I think, a very nice bio-based entry point for the chemical industry. And in the end, this goes to materials, and these materials, they have a lot of, let's say, properties, a lot of quality demands, and they are pretty stringent. You can think about packaging, or cables, or car interiors, or let's say isolation stuff, etc. But the properties must remain the same. So you can go bio-based, yes, but in the end, we want the same chairs, the same tables, etc., and the same car interiors without any quality deterioration. And that's, of course, a very good challenge. An example is, I like this picture. I was some time ago in the Stedelijk Museum in Amsterdam, and then they had a nice exhibition about raw materials. And this is a picture taken from two sides by me, and this represents the raw materials of a Beetle car. And what this company did is, these are really artists, they really took a Beetle car, they took it apart completely and separated all raw materials and collected the raw materials in these cubes. And this is then presented. They did a lot of other stuff, other user goods, but this is the way it goes. Now, the nice thing is that they also add, let's say, a list of raw materials in weights and kinds. And this list you can well, we have an educated guess. What is the carbon footprint of each raw material of this list? Iron ore, must be, for instance, gained in a mine, purified, transport over the world, go to steel making, do a lot of things over there as well. So it has a pretty high footprint. And if you add all these things, then you see, in fact, you get a list, and then you could already conclude that about 95% of the weight of that Volkswagen Beetle came from fossil resources, only 5%. And the carbon footprint is caused by 99.5% of fossil resources. Yep. So this is, and then in the end, on the right bottom side, you see two figures, and then this concludes, in fact, that 1 kilo of that kind of car will be about 10 kilos of CO2 in the atmosphere. So what is now the road to circular materials, and how does circular complement bio-based? I like to put this into this picture, and again I was inspired by also a former colleague Gerard de Weremeus-Buning, and it says that in fact when you start with a fossil raw material, you start with a carbon footprint of 3, I come back to this number, it's a very easily derivable number, you create in the first steps of the chemical process, you go from fossil raw materials in the end to user goods, but in the beginning you create a lot of footprint and you do not create a lot of value. And when this process proceeds, then you create more and more value. So until you get your good. So if you are combusting it, that is what we do today, you destroy in fact value, you just recover a little bit of energy, but that's really not much. What you can better do is go bio-based. You can at least make fossil, make naphtha or base chemicals or monomers from bio-based, and then you win already at least 3 kilos of CO2 per kilogram of product. You can also mechanical recycle it, it's the blue area, the blue arrows, and on the top right, you can do a little bit fierce, the chemical recycling, then you really take the monomers apart, etc. And in the end, you can do it even more fierce, and that's almost burning, but now we leave out a little bit of air, and then you have pyrolysis and gasification. And this is how, in fact, circular recycling and bio-based complement each other. And what you make sure that you create most of the value. If first to go bio-based, then you can reduce your footprint, but you can really also maintain your value by the recycling. Keep it up as much as you can. This is, I would say, the way we can really, run this planet, so to say. Okay, so what does a sustainable world look like? What are the basics insight I gained, and these are all open for discussion, by the way. But these 5 items do at least make sense to me. First one, in a sustainable world, I would say energy should come from energy sources, and materials should come from material sources. And I think that sounds very logical, but for instance, trying to make products from electricity is in fact economically less attractive. That is what I found out. Again, during a lot of discussions with other people. Energy is by far the cheapest sustainable source. The electricity is by far the cheapest sustainable source. That's also very important to know. It's also very good news, by the way. So you should maximize electrification. Of course, there's one exemption. Electricity takes batteries. Batteries are heavy, and you cannot take it into the air. This calculation doesn't fit. So you really need the let's say the kerosene, the fuel for air flight, aviation. But these can be made from bio-based source, but it's only a small amount related to the total fuels we are currently using in the world, about 7%. Materials, also very good news, and that's not only my opinion, that's opinion of a lot of other experts around the world. There is enough material available. We have to just make them accessible by suitably commoditizing it. Feedstock to materials is cheaper than power to materials, I said, and as an example, in the next slide, I will show you that you can make hydrogen from biomass and hydrogen from other sources. You can compare them. Hydrogen is very important intermediate for methanol, for ammonia. Ammonia goes into other products, methanol too, etc. But if you're looking at this slide, and again, there are much more extensive studies available with much more technologies to be prepared. But this one I could create because I know a little bit about green hydrogen from electricity. Also, I had a very good discussion with Torkol and Torgas, and also with call it the Bri2 project. Claiming in fact that hydrogen from biomass is very interesting, and not only in cost price, which is about the same as the current cost price at maturity, but especially also in carbon footprint. And why? Yeah, because you are using biomass. You are using fatal biomass even, and this fatal biomass you prevent this fatal biomass from rot, etc. So you will gain a lot of CO2 instead of losing it. So you will take CO2 out of the air instead of putting it in. And that means that the footprint is negative. And that's what you see when you use this route. Yeah, so again, it is not carved in stone, but for me, all this evidence is, let's say, piling up, and I really would like to see new projects coming with green hydrogen. So if you are going from bio-based value chains into products, you start with this biomass. Very broad, can be anything. Nitrocellulosic, natural oils, and the whole list I just showed you a few slides ago. This biomass should be treated in such a way, that the most valuable products you take out first, like the crops, like the proteins. That is normal agrochemistry of agricultural, I would say, operations. But you will always, let's say, at the end, you will also always have residues in your hand. And these residues that you can commoditize and separate into, for instance, feedstock for chemicals, which are typically, let's say, carbohydrate or acids, natural acids, or you could make soil improver, also carbon, as carbon really, or salt. And what you do there is on the farmer level, you have a typically small scale operation. You do your crops, and you process your residues, and you give it a mild treatment. It's mostly mechanical, like sieving or like milling or like filtering, etc. Meaning aqueous, low temperature, no acids, no bases, no chemistry. That it's very cheap. These plants are really, I would say, inexpensive, related to the steps after. Then you bring together, your residues to a typical chemical site, and there you do the chemistry. And why? Because of economy of scale. Because these installations are darn expensive. You use solvents, you use acids and bases, you use high temperatures, high pressures, and all that must be operated in this plant. So that's why you bring this together. But for bringing it together, you need to transport. You need to commoditize. The chemistry would like to have all year through access to the same quality of raw materials. That's the way we operate, and that's possible. But you need to commoditize. It has to be of course, good price. But if you are making it more dense and the logistics become cheaper, you can in one lorry you can take much more kilos of biomass if it is densified than when it's not, and then you can make some good economics out of this. And examples of commodities, let's say from the whole picture list I showed you a few slides earlier, you can think about pellets, wood pellets. You can think about oils like naphtha, bio-naphtha, or melasse, when it is sugar. And these are just depicted on the left bottom side. Taking just an example, we have lignocellulosic biomass. That's, I think, the feedstock which is most abundantly available on Earth. It has typically three elements, like hemicellulose, left side, cellulose, right on the top side, lignin on the right side, and some other materials which can be proteins, extractive, organic acids, or ash on the bottom. And from each intermediate, so to say, you can make different products. For C5, you can start with, not much value, humans char, but you can go to furfural, you can go to sugars. Or C6, you can take sugars, but you can also make chemical products out of this. Right hand side, you go from char to aromatics. And in this way you can make your own refinery, which is most, I would say, let's say the product package you need to make, which is most interesting. That's I think a very good thing to figure out. And the good news is you can have really great economics out of this all. So opportunities is also to valorize the smaller, the less voluminous substances in lignocellulosic biomass. Yeah, you can also think about sugar valorization. Also there we have a lot of potential, especially from sugar beets or cane sugar or maybe lignocellulosic sources. But you see, if you have the volume versus sales price graph in front of you, by far most of the fermentations is ethanol for fuel, for mixing it with your petrol. And you see also that the value is not all that great. Here it is 600. I think nowadays it's $700 to $800. But this is, I would say, already pretty expensive. You can make if you do it via methanol and MTO, methyl olefins or methyl fuel by Fischer-Tropsch. Most probably this number will be closer to 400 than to 800. But on the left-hand side, you see still basically a lot of fermentation products which are still interesting. I investigated already in the past succinic acid, as told in the introduction. But you see here there's a lot more of valuable materials you can make, you can create from sugar by fermentation. And this is just an overview. So I think also fermentation is, I think, a very important area to green your processes, because they use sugar anyway. Now I come to this example of this deeper dive. I will not dive too deeply with you, otherwise we will run out of time, of course. But first of all, I would say I really like this picture because from wood you can, from the sugars from wood, you can make livolinic acid in an astounding, I would say, efficient way. About 7 out of 10 sugar molecules are converted to livolinic acid via this very comprehensive scheme, while also co-producing char and formic acid. And this can lead to a lot of value creation, and this is what we would like to, what we also investigated in DSM, and we came with this kind of process. You come in with biomass, You will add some acid and some water. You cook it, like in the paper industry. You make your levulinic acid. You separate your char. You extract your products, and you distill them off, and you make levulinic acid, organic acids, and formic acids. And of course, the cheaper the raw material becomes, the cheaper your product will become. Yeah? And that's also what we really recognize in DSM. We don't like to use fructose because fructose is very expensive, and that means your levulinic acid will be expensive. Pulp is better, but not good enough. If you go to woody biomass, especially the rejects, like the residues, etc., the pins and fines or the bark, which are not not much value, then you can really come up with very cheap levulinic acid. And then you can create, I think, also a nice value, and that's also depicted in this graph. When we start with commoditized biomass, which are already rated at €120 per ton, which is, I think, a fair price, and make, via levulinic acid, formic acid, and biocoal, you make biochar syngas, you make C6 monomers via a number of intermediates. And you see on the red figures, the volumes and the energies and the value, then you can easily deduct that you have a lot of value creation, about 250%. Every dollar you put in, every euro you should say, you put in, you create €2.5 of products, which I think a very good starting point for a business case. And why? Yeah, because your energy yield is very good. 50% is a marvelous energy yield, and the carbon yield is really great. Yeah. And that makes this value creation possible. Well, if you talk about C6 monomer, think about dimethyl adipate, you can go all kinds of directions to materials. You can make HMDA, hexamethyldiamine, you can make hexanediol, you can combine it to nylon 6,6, but you can also combine it with other intermediates, to other polymers, like polyurethanes or diisocyanates, and these can be applied in polyurethane coatings, adhesives, elastomers, etc. Yeah, so this is, I think, very nice, and this is a very active project in Insight, I would say, and really we try to interest the industry for this. So if you look here on the left-hand side, you see effect from top to bottom, let's say a value chain towards materials from fossil feedstock. The green ones are the bio-based equivalents. Not exactly the same materials, but really resembling. And what we like to do is make ingredients and coatings, adhesives, sealants, elastomers, etc., and make building blocks from engineering plastics. And we like the driver, to go from fossil to the bio-based is, of course, cost. Often cost and sustainability go hand in hand, and performance. And just a comparison, you can compare gamma-butyrolacton with gamma-valerolacton. The difference is one carbon atom, but the applications are, I would say, similar. And in this graph, you see on the left-hand side that the fossil value, based on a number of assumptions, will be the cost will be €1.44 per kilo. If you make this renewable, at 550 kilotons at the same scale, it would be about half of the price. And why is that? Because you make a biorefinery. You create a lot of other co-products which have value in the market. So that is the secret of the value creation. And this makes it possible that you start from levulinic acid to make some intermediates which can already have nice applications, and you can grow towards bigger products like caprolactam, adipic acid, hexamethyldiamine, hexanediol, etc. Just one slide on chemistry, because it feeds the next slides as well. So we developed in DSM, in 2010 to 2013, This process, starting from woody biomass, levulinic acid, we hydrogenate it to gamma-lacton. We ring open it to methyl pentanoates, the 3 isomers, and then we to make an hydroxycarbonylation to dimethyl adipate, and then we can simply hydrolyze this to adipic acid. And if you are seeing how the adipic acid is made in the past, it comes from natural gas, crude oil or coal. You have several routes to adipic acids. When you put the renewable adipic acid to it, then you see that sugar or levulinic acid can be very good intermediate. I think sugar was some time ago a hype. I don't believe it's really possible with sugar. And then you can start with the interaction. And the idea is that you're really slowly starting to replace intermediates with bio-based and greening up the processes in this way. And you see that gradually your adipic acid can become green. Another way to represent the attractiveness of chemical pathways to bio-based and circular materials is this. This is a triangular phase diagram with at the edges, we have on the left bottom corner carbon, on the right bottom corner hydrogen, and to the top corner oxygen. And in this triangular diagram you can represent your softwood. It's not one point, it's really an area. The middle gray circle is softwood. If you take this softwood apart in humans, chars and glucan, it kind of explodes. And the glucan, that is the feedstock for levulinic acid. And nice is that you can really construct in this diagram your pathway towards adipic acid, starting from glucan, levulinic acid and formic acid, but also gamma-lacton and methyl pentanoates. And you can continue with the red one. I changed color because of clarity. You can go via this methyl pentanoates, dimethyl adipate, to adipic acid. And what you see is that the pathway is very short, meaning you don't have to oxidize a lot, you don't have to reduce a lot, you don't need too much additional raw materials, and you come to this. And by the way, I was also inspired to make these triangular diagrams because of the work of Thomas Farmer. He is in New York University. He presented a very, I would say for me, impressive presentation where he has also similar presentations. Yeah, if you compare this with the fossil equivalent, then you would start with reformate. You go to the left bottom to benzene, then you go back to the right to cyclohexene, then you go to Ka oil, and then you go to adipic acid. This pathway is about 3 times as long, and it needs also a lot of additional chemicals, and that's why it is relatively expensive. So you can compare the two. So you see that really the pathway of the green pathway is a lot more attractive than the red one. And this you can see back in let's say variable cost. We really developed in DSM a model for that, which is of course very indicative. There's a lot of big database on top of it, but you see that the cost price of cyclohexane based or phenol based adipic acid is around, let's say, €1. You can green the cyclohexane and green the phenol, and then you have a little bit advantage. But if you are going to reconstruct the whole chemistry and go via, for instance, levulinic acid, you will have the best cost. And that will be about half of it. And nice news is that the same holds for carbon footprint. Often cost and carbon footprint are interrelated. So also there, you see that levulinic acid and sugar are really very, very interesting. And you would expect, because of this, that the market share of phenol-based or cyclohexane-based adipic acid will decrease on behalf of the sustainable routes. And of course, the speed depends a lot about the policy. The more green the policy is, the faster it goes. Now also the whole database, we can really see that that we can make some kind of predictions. We had about 60 molecules we considered, and on the y-axis, on the vertical axis, you see what kind of more renewability we could expect every year. So the higher the bar is, the more the process is prone to transition, right? So we just discussed, the caprolactam, adipic acid, adiponate, nitrile, etc. route. But you see there's a lot of more opportunities. So you see there's a lot of greening of potential going on there. Yeah, it still didn't happen. And why not? That is of course the famous valley of death. You need a lot of money to build your plants, to do the piloting, etc. It takes too long. The incentive is not there. There's no partners which can really go with you. Supply assets, nothing to offer. That is where a lot of projects stand now, I would say, on the bottom of the valley of death. I mean, it's not a very positive news, I would say, but I think we are really in the beginning, of this transition, and we should really do our best to make things happen. And we can do it. If you are commercializing the LA tree, you think about technology and manufacturing, of course, but you also think about customers. Without customers, you can really forget everything. So that's your core. You add your partners in energy, in raw materials, in technology, and you need also a lot of support from all kinds of groups wanting society to make this happen. And we see now there is some movement. We have a very nice advice of our social economic council in Holland. But in the end, you need this open innovation. That's really what you need. Excellent environment to make that happen. We are very well equipped in Holland, at least in this area too, in Camelot, Brightlands, to work on this. And we can really bring together partners across the whole value chain. And that's what we need to make it happen. And from a technical perspective, I keep saying it's possible. We don't need time to 2050, not at all. We need 15 years. If we technologists can say this, 2035, we can do it. But then all the lights must be on green. That's for sure. Question is, of course, who wants to become a player? And also my opinion is that also such directions must be governed. Must be set out by governance. So you cannot ask industry, please green up your process. And then they said, yes, we do, and in 10 years you're done. Looking at the chemical process, chemical industries, we have typically, example Camelot, but I'm sure there are more sites like this. Natural gas and fossil naphtha are our feedstocks, main feedstocks. How to green them? Now, of course, you can start with, let's say, for instance, refuse-derived fuel made from what you throw away at home. You can torrefy it, and you make a char, and this char you can gasify, and you will have your hydrogen. That's the way. A second way, there are more, is that you use plastic waste. Also, in Sabikte we have some nice examples from this. Catalytic pyrolysis, making char, also making liquid naphtha. Or you could say, now, like the linoleic acid case, you start with primarily biomass, or a biofeedstock, etc. Catalytic conversion directly into chemicals and char. And this char you can gasify again. And in the end, you can just make the circle complete, make the transition complete, and be independent from fossil resources. So for Camelot, it looks like this. We have no natural gas naphtha. We make hydrogen ammonia from this. From ammonia, we make caprolactam acrylonitrile. From naphtha we make ethylene, propylene, pyrolysis gas. Ammonia you can make fertilizers, melamine, carbon dioxide comes also with it. Polyamides and polyolefins. Now, how to green it? Well, we can start connecting with biomasses. Then, we can make the intermediates green, and then you see that in the end of the plants, let's say the ammonia plant or the fertilizer plant, etc., they can stay the same because you just replace their feedstocks. That's all. That's the good news. You don't have to build the plants up again. We can make the assets, keep using the assets. And in the end, perhaps in 2050, that is ambition at least, we are completely green. So what will happen? Well, I would say what needs to happen, and that's really innovation. Innovation, innovation, innovation. That is what we should start now. How? We have to find first new circular sources, bioresidues, solid waste, etc., and to commodify them. Develop new processes to this. And this means making commodities. Something what the chemical industry can use with the same quality, but preferably than the current raw materials. And then you select the best chemical circular process opportunities, both LCA, liquid life cycle assessment, and economics. And these both often go hand in hand. And we can compare it with the current state of the art. But now I'm stating now at level playing field. I come back to this later. Because we must have a fair comparison with fossil industry. And if fossil industry can just get the oil for free out of the ground, then it is always, fighting against the Goliath. So this should not happen. Then start manufacturing circular intermediates, replacing fossil, again, level playing field, and gradually increase. So it is gradually. It's not a one-time thing, it's gradual. And then you can go to 100%. So all conditions to boost innovations are satisfied. I mean, we have really the people in place, we have the knowledge in place, we have Holland is a very knowledgeable country, I would say, Europe too, by the way. And but except one thing, in my opinion, is we need innovation financed. And innovation is not only doing an experimental lab scale, but also piloting, building plants, scaling up, and making the economy really boost. And this requires, according to the chemical industry of Holland, about 65 billion over the coming 30 years. You could say, well, a hell of a lot of money. I'm saying, no, not at all. It's only 2 billion a year, which is less than 1% of our gross domestic product, which is, I think, a no-brainer, I would say. Yeah. So again, going back to the level playing field, what is now a level playing field CO2 price? Nowadays the CO2 price is around 30 euros per ton, right? Is that level playing field? Answer is no, but I will show you. But how to calculate it? And that's I like to use this example. An airplane must fly on fuel, liquid fuel. There's no way around it. I mean, I think everybody agrees. Fuels should taken up in the air, must be light, etc. Energy intensive, meaning it is CH2. It is kerosene. Yeah? Kerosene, you can has a molecular weight of say 14 CH2. They make CO2 out of this. It's 44. 44 over 14 is about 3. Now that's why where the footprint of 3 of oil comes from, because this is this ratio. So if you are using mineral oil, you make jet fuel out of this. You're talking typically from $40 per barrel to 400 euros per ton, the blue entry. If you do this from biomass, which needs to be done if you want to make it green, then you start with 120 euro per ton for the commoditized feedstock, and then you end up with about 1,000 euro per ton. Difference is $600 per ton. You divide it by 3 because of this molecular weight, so that the CO2 price at this level playing field is 200 euro per ton. And that's about 7 times more than currently. So we know where we're heading to, and other countries do too. Also Canada is very active on this. They are already, I saw some publications with this kind of price. You say, well, that's a lot, because now flying becomes a lot more expensive. I said, well, of course it will become expensive, but I think it is also very affordable. Think about 30 euro per 1,000 kilos more because of the CO2. And that's only level playing field. So if you would like to boost your biobase, you should really go beyond level playing field, making biobase very attractive. So what can we do? Yeah, I would say join forces and collaborate. Find owners driving this transition. Provide supporting, stimulating means for this. Make this level playing field happen. That requires some policy decisions. Preferably globally, but at least in the EU, I would say. Develop competitive binary refinery concept with maximum value creations. Now there the technologists among us have a nice assignment. And giving these bulk intermediates a constant quality, availability and price. And of course minimize energy consumption and involve society in all steps. I can have a whole story about Staatsbosbeheer and Greenpeace, but I think it's very good and to have them on board. So, finally is just join forces and walk the talk. And I'm now talking about especially the younger people from the audience, because you, in your professional career, can do a lot more than I can at my age, right? So team up in processing circular feedstocks, best biorefinery concepts, establish circular value chains, connect to the partners, make sure all the partners in the whole value chain are there, jointly prepare business plans and really collect, the right, the best value creation, I would say, make plans attractive for financing, and set up and execute projects. So both Camelot Insights and InnoSyn, we can both take a very good supportive role in the piloting infrastructure and providing the knowledge. And that's why I would like to thank you for your time. Thank you.
Thank you so much, Marijn, for your great and very inspiring talk with a very positive conclusion for sure. Technically, it seems to be all possible. Let's just make it happen, and there's a good basic here for open innovation. So let's go to the chat, and there are a lot of questions which will challenge you sometimes as well in your vision.
Yep.
So Ingrid, you can start with the first question, okay?
Yeah, I'll get a little bit nearer the microphone. Marijn, thank you so much. I've known you for a few years now, and you've always been really passionate, so I'm really happy to be sharing this with more people now too. The good news, we have a lot of alternatives, it is affordable and we can speed up, so really positive message. What we saw in the chat, what people already very actively using, answering each other's questions also, so that's really good to see this interaction. And we will look into some of the questions a little bit deeper with Marijn. Marijn, a number of questions were asked about the production of fertilizers. Can you elaborate on that a little bit more? The production of fertilizers is very energy intensive. Has this been taken into account in circularity?
Yes, Okay, it's a comprehensive question. If I look at the fertilizers produced by OCI at Camelot, then their raw materials, I would say, is basically ammonia. And green ammonia is really exactly the same ammonia than grey ammonia. So this means that from this quality of ammonia to fertilizers should not make any difference in cost if you do this from green or grey. That's maybe a very easy answer because it could very well mean that the fertilizers are, well, we can also think about fertilizers from other sources, from more bio sources. And yeah, this is then a question about economics. I mean, I'm not saying at all bio-based is in all variants good, not at all. There are some bad routes bio-based, and there are some excellent routes, and we have several ways. So that's why in this livolinic acid example, we already investigated 10 routes in organic chemistry, and 20 routes in organic chemistry, another 10 routes in fermentation, and by finding then the best. So that's important because there are some routes which really do not work, or they are very expensive indeed, or they require a lot of even in bio-based, they can still require a lot of hazardous chemicals like heavy metals or something like that. So this is, I think, so as I would say, economy is always distinctive, but so you have to find the right process. Once found the right process, if you have the same intermediate, which you can make bio-based and fossil, it doesn't really matter.
Okay. Well, there's also alignment with the other question, and you already answered that in this answer a little bit more. Are the bio-based materials lesser in quality as a technical fact, or is this mostly a perception people have?
Yeah, this is, it is certainly not to be underestimated. I mean, fossil feedstock is really very pure, very well refined, and it is also, you know, a consequence of about 1 century of development. So the quality of the naphtha which comes to Camelot is really within a very narrow range. Yeah? If you go bio-based, then you should also define an acceptable range, because in the end, I'm really sure materials we cannot, let's say, we do not want to have lesser quality, you know, tables and stuff we are using. It must be the same. The touch of say a leather or something like that, or some plastic material, engineering material in the cars must be the same, and that's possible. But you need to, and it can be distinctive, I should say. Yeah.
Yeah. So there was a question about bio-based, the quality you just answered, also the price, but there's also a question about the scale of the supply of biomass, for example. Yep. Can you go into depth on that question?
Yeah. Well, taking, for instance, Camelot as example, I think it's a nice example. So we don't see the raw materials coming in Camelot because they are coming via pipes between the Ruhrgebiet and Antwerp. This is not, bio-based cannot go via pipes. Maybe oil, but certainly not the lignocellulosic. That must be trains or trucks. And yes, you will see it. That's for sure. It's possible, but you can think about, let's say, 1 truck every 2 minutes or something like that. If you want to serve, you know, the bio-based needs of a site like Camelot, it's a lot, but it's possible.
It's okay. This means a different way of transportation of goods, of supply. Yeah. But the quantity, is that a problem? Do we have enough wood, or how do you? Is there a challenge also to go?
always a challenge, but again, in the world there is enough. In this area, there's not enough. I mean, Camelot is a very big site, and I think we need about maybe 100 kilometers around to draw in all the feedstocks, which is of course not possible. But in the world, in Africa, in Brazil, in Canada, there's a lot of biomass, which is just wasted, nothing. And if you are making them transportable, and I think Torgas and Torkol thought very well about this, you can make some kind of a bio-charcoal logistics, and they can come with boats and like in hoogovens. They have also, or let's say electricity power plants. They have a big coal logistic. Well, I don't see whether that's not possible in Camelot.
Okay. So we need to work together. That's also
that is for sure. You need to team up with all the partners in the value chain.
In the value chain.
Yep.
Okay. Did you pick another question?
Yes, I did. Also about I see some questions also coming from the industry interested in transforming processes, and a question about upscaling. How rigorous are the technological models to create large-scale plants and hence derive realistic economics?
Well, how rigorous are the technological models? Yeah, I think they are quite. I mean, the scaling up for bio-based processes follows the same kind of pathway, the same kind of competences as scaling up fossil processes. I don't see any difference there. Mm-hmm. Of course, handling the solids, that's with lignocellulosic biomass. Yeah, that's of course a thing which must be challenged. This can be challenged, but the paper industry does it every day. So I'm not saying is it impossible. It just requires innovation, and I'm quite sure we have a lot of talented people in this area. We have a lot of organizations in this area which can really drive this. The only thing is, there must be a boosting force for this. Somebody would like. There must be some owner. Society should be the owner. Mm-hmm. Do we want heating up the earth? Everybody say no. Okay. Do you want to take the consequences? Everybody would say yes. And then, you have means to innovate.
Yeah. There's maybe a bridge.
Yeah.
There is a bridge, I think, to another question. Is there currently, and can you say something about it? Of course, it's also a consumer pool, but what is currently accepted as commercial price addition as a green premium? Is there? Or is it really the industry, it just must be competitive and there cannot be a green premium? Can you say something
we touched upon this a lot in the past. I would say, my opinion, personal opinion, green premium is maybe nice, to start your business, to make some space. In the end, there must become like in the rest of the world, price competition. But make this competition on a fair basis. Let's say we can talk about green premium. I don't hear anybody talk about grey premium. Well, grey premia are imminent because countries allow that companies are getting the oil for free out of the ground. What's that? That's a grey premium and not a small one. So then I would say just leave out the green premium and the grey premium and make a level playing field. If that happens, you should really see how fast it can go.
So the play field should be more honest than it is right now as well.
Yes.
It's not honest at all. We have 2 minutes to go. I see some very concrete questions. Do you have a particular one, Ingrid?
Yeah, I see some very detailed questions about the...
Please take the mic. Take the mic.
I see some very detailed questions about the levulinic acid. How's the status of the commercialization
Yeah, well, we
that
are in Insight, we are quite in the middle of it. So we are having a pilot plant fully operational for showing this process, and also in Brightlands we have a lot of contacts with potential customers who are really interested.
Okay. That's also a good bridge to my next question. What do you advise companies, industry now watching, wanting to know more, willing to test their new processes?
Contact us.
Yeah.
No, really, we can help, and of course we have to again. Society should want it. Industry can execute it.
Yeah, and we have the facilities here to test.
Yep.
At a,
we are very well equipped. Yeah.
Yeah.
And the nice things in going green is it creates an awful lot of jobs. I talked about 2 billion a year. This means 20,000 highly qualified jobs on all kinds of levels, all kinds of competences, technically. So that's really great. It's a really opportunity. I mean, sometimes, industry saying, well, going green, that costs jobs because we have to close down my refinery.
Mm-hmm.
You will get back 10 times more.
Yeah. So it's planet, people, and profit.
Exactly.
Exactly. Okay.
I would say people, planet, and profit.
People, planet, and profit.
Yeah.
Okay.
Yeah, let's wrap it up. It's everybody can count. When you ask 6 billion, I believe, and the first year is already 2 billion coming up for new jobs, then maybe we just get started. But if it was so simple, then for sure there are a lot of challenges to go. We for sure did not answer all questions because there were a lot, but you already said you can always contact, the details are in the slide behind me. You can always contact Marijn directly or just give the campus a call, and we'll make sure you get connected. Thanks again for your great talk, a great inspiration, and hope to see you all soon healthy and live back at Brightlands Camelot campus.
Yep.
Stay safe. Thanks.
And thanks a lot for having me.